Okay, so back to the hypothesis test. We start by stating our parameter. So that is the P1 minus P2. And it will always be equal to a true difference. But then the context depends on the next part. So it's a true difference in the proportion, or I'll say in proportions of Black / Hispanic females in STEM and non-STEM programs. Ooh, sorry, I'm writing kind of tiny there. Okay, so I do want to emphasize that we are doing STEM minus non-STEM, right? The way that we subtract is going to be important. In this case, if the proportion of Black or Hispanic females in the STEM program is larger than that of the proportion of Black or Hispanic females in non-STEM, then this will be a positive number. If the opposite is true, if the proportion in STEM is less than the proportion in non-STEM, then this will be a negative number. So it's really important that I specify which way I subtracted. So then my statistic is P1 hat minus P2 hat. Okay, so they didn't actually give us P1 hat and P2 hat. We actually have to calculate those. So let's go ahead and do that. P1 hat is going to be the number of Black and Hispanic females in STEM. So 12 divided by the total number of STEM students, so 300. And we just divide that real quick. Let's see, 12 divided by 300 is 0.04. Okay, so that is my first sample proportion. And then to find P2 hat, I'm going to take the 75 Black or Hispanic females out of the 500 total non-STEM students. So 75 divided by 500, 0.15. Okay, so I have my two individual sample proportions, but my actual statistic is that I have to subtract them. So 0.04 minus 0.15 is negative 0.11. Okay, again, it's important that I noted that I'm subtracting this way. If I switched this, it'd be 0.15 minus 0.04, and that would be positive 0.11. Okay, important to note which way you subtract. So then my hypotheses, okay, so I've got H0 and H1. My null is always an equality, remember? So I have my parameter P1 minus P2. That's going to show up in both of them. It's going to be equal to something for the null. Now, let's see. The baseline is what we try to make our null hypothesis, right? So the baseline here would be that there is no difference between the two populations. And that's going to be true for pretty much all of the problems that we do for difference in proportions in this class. We're always going to assume there's no difference between the populations. So there's no difference. They are equal to each other. P1 would be equal to P2. Okay, so we can rearrange that. If we subtract P2 to the left side, we'd have P1 minus P2, and on the right side, we would have 0, right? The difference between them is equal to 0. So 0 is our null value. It's also going to show up over here, but we need to decide what kind of inequality we need for our alternative. So we go back up to the problem, and it says, evidence that Black and Hispanic females are underrepresented in STEM programs. So if they're underrepresented in STEM, that means STEM is less than non-STEM. So we're going to say I'm going to go ahead and write that one. P1, so STEM's proportion of STEM students is less than the proportion in non-STEM programs. If I rearrange this, subtract P2 to the other side, I'll get 0 again on the left side. So we say P1 minus P2 is less than 0. And it's always probably just kind of a good idea to check and make sure your sample difference supports your alternative, right? This is a negative number, that would be less than 0. So we are supporting our alternative, which means we do have some evidence. We're just going to determine whether or not we have convincing evidence in this hypothesis test. Okay, and then we need to put our significance level in there, which it told us a 5% significance level. We convert that to a decimal, so alpha is 0.05. Okay. So let's move on to something a little bit new, the name of the procedure. In all of our previous procedures, they were always one sample. We have two samples now. So our procedure is called a two sample. And then it's still Z because we are able to use that Z test statistic for proportions. And it is a test. So two sample Z test for, it's no longer just for P, it's for P1 minus P2, the difference in two proportions. Okay, so now we need to check our random conditions, and there's a little bit new here too. We still have to check that random condition, but now we have to check that each sample is random. So I look back up at the problem and it says they took a random sample of 300 STEM students. So I'm just going to quote that. Random sample, R.S for random sample of 300 STEM. And they also took a random sample of 500. So random sample of 500 non-STEM students. Okay, that random condition is met. What's new for the difference in two proportions with this is that not only do they each have to be random samples, but they have to be independent of each other. There can't be any connection between the STEM student in this sample and a non-STEM student here. So I don't really know of any way that you could connect them, but one way that you could take dependent samples that are not independent of each other would be to say maybe do like a before and after for a person, or maybe you could find roommates and one was STEM and one was non-STEM. I don't know. It's a little bit hard to envision in this example. So these are independent of each other. Independent samples. We also have to check that. Okay, so then we check the second condition, the 10% condition, and I've had a lot of questions on this recently, so I'm going to try to go through it a little bit slower. I have to do it for each of my samples. So sample size of the first one is 300. Now, what I want is for 300 STEM students to be less than 10% of all STEM students, at this certain university. So if 300 is less than 10%, it'll also be less than 1/10, right? 1/10 and 10% are the same thing of all STEM students. Now, in order to check that, I actually could write out the computation I'm doing, but because multiplying by 10 is so simple, I normally don't. So what I'm really doing is I'm getting rid of this 1/10 and multiplying by 10 on both sides. So 300 times 10, I just add a 0 to the end. But if you're not sure, 300 times 10 is 3,000. So I ask, is 3,000 less than all the number of STEM students? Well, if we're at a large university, or really even a medium-sized university, 3,000 is probably less than all the STEM students. This wouldn't work for Fontbonne, but we're going to say it does work for this university. So then we do the second one, and 2 is 500, and we want to know if that's less than 1/10 of all non-STEM students. Okay, so again, I multiply my sample size by 10. 500 times 10 is 5,000. So is 5,000 smaller than the whole population of non-STEM students? Again, at a large university, that would be true. So those two conditions are met. Okay, so then the third condition is to see if we can use a normal model to model our sampling distribution. So we check the large counts condition. And this is where we have to do those 4 different calculations. But the good news is usually they're already actually done for you because they give you the number of successes. So we have to do N1 times, we would want to do P1, but we don't actually know what the true population proportion is, and we're not even hypothesizing what the true population proportion for STEM students is. We're just hypothesizing that there's no difference between the populations. So we actually do have to use this sample proportion to estimate it here. So N1 times P1 hat, okay, I could literally do 300 times 0.04, but guess what I get? 12, because this is the number of successes, or the number of actual Black and Hispanic students. So I am just gonna know that that's 12. Then I have to check N1 times, not P, but Q1 hat. So if 12 of those STEM students were Black or Hispanic females, the number of students who were not Black or Hispanic is the sample size minus 12. So 288. 300 minus 12 is 288. If you want to, you can say, okay, 1 minus 0.04 is 0.96. Multiply that by 300, 288. Either way is fine, okay? Then I also have to check that for the second sample. So N2 times P2 hat is going to be, again, the number of Black and Hispanic females for non-STEM students, which it said was 75. And then N2 times Q2 hat. This is going to be the non-Black or Hispanic females in the non-STEM students. So 500 minus 75 would be what? 425? Or again, you could take 1 minus 0.15, which is 0.85, and multiply that. 0.85 times 500. Either way, you get 425. So I look at all four of those values, 12, 288, 75, and 425. Those are all greater than or equal to 5, so my large counts condition is met. Okay, so before I move on to the do and conclude sections, I'm going to go ahead and end this video and make a new one.